What if the reason your smaller AI models are failing at complex math isn't because they lack parameters, but because, well, you're accidentally forcing them to memorize the teacher's stylistic doodles instead of the actual equations?
Yeah, that's exactly what's happening.
Right. Welcome to AI Paper Slap, the series where we break down the latest AI and machine learning research for practitioners building, the next generation of models. We're jumping straight into the core of today's paper. It's called On-Policy Delta Distillation, or OPD2, from researchers at Naver AI Lab.
It's a really clever approach.
It really is. So standard on-policy distillation, or OPD, trains a student model by forcing it to imitate a teacher model's outputs. But this paper proves mathematically that this is highly inefficient because you just end up copying all the teacher's baseline stylistic quirks.
Right, all the extra baggage.
Exactly. So OPD2 flips this completely by using a delta signal, which is the mathematical difference between a reasoning-tuned teacher and its own base model. By distilling only the knowledge acquired during reasoning tuning, smaller models, like a 4 billion parameter Qwen3, achieve these outsized gains in math, science, and coding.
It's impressive.
Oh, for sure.
No
It effectively beats standard 8 billion parameter models and does it in a fraction of the post-training time.
Yeah, and if you're an ML engineer currently bashing your head against the wall trying to align a model, post-training is your ultimate bottleneck right now.
Oh, yeah. The absolute worst.
Right, because you're constantly fighting this battle between supervised fine-tuning, which is stable but, hits a ceiling really quickly, and reinforcement learning, which requires this incredibly complex, noisy reward design.
And nobody wants to deal with reward models if they don't have to.
Exactly. So what OPD2 offers is this highly practical middle ground. You basically gain a method to unlock those RL-level reasoning improvements, that deep, rigorous logical capability, without needing a flawless reward model. You just extract a pure reasoning signal directly from the teacher's own learning trajectory.
Right. And to understand why extracting that specific trajectory is such a paradigm shift, I think we need to look at the mechanics of standard on-policy distillation and, where it breaks down.
Yeah, let's get into the math.
So the baseline formula most of us use in standard OPD is log pi star minus log pi theta. Basically, the log probability of the teacher model minus the log probability of the student model.
Right, and that's applied practically at the token level on the student's rollout samples.
Okay, so on what the student actually generates.
Exactly. You give the student a prompt, it generates a sequence, and then you use the teacher model to score those specific tokens. The objective is to minimize the KL divergence between the student's probability distribution and the teacher's for those generated tokens.
So if the teacher likes a token, reward it.
Yep. If the teacher assigns a high probability to a token the student generated, you enhance that behavior. And if the teacher assigns a low probability, you degrade it.
Right. But, and this is where it gets interesting, the researchers at Naver spotted a fundamental flaw in that standard approach.
A pretty big one, yeah.
Yeah, because a reasoning-tuned teacher, say like a highly advanced math model, it didn't just spawn into existence knowing calculus, right?
Yeah.
It started as a base model, pre-trained on a massive corpus of general internet text.
So it's got a lot of internet habits.
Exactly. So that teacher retains all the natural conversational preferences and stylistic tendencies it had as a base model. It knows how to predict the next word based on internet grammar, not just pure logic. Standard OPD blindly forces the student to learn all of this redundant, non-reasoning noise.
Yeah, which is super inefficient.
It's like copying a brilliant professor's complex math equations off a chalkboard to learn calculus, but because you're blindly copying every single chalk mark, you accidentally copy their messy handwriting, the way they cross their sevens, and the random doodles in the margins. You learn the math, but you're wasting parameter capacity on the doodles.
That's a great way to put it. Because the target knowledge we actually care about during this post-training phase is the reasoning ability, right? Not basic next token prediction.
Right.
But log pi star contains both. So you are forcing the student network to spend its gradients mimicking stylistic preferences that don't actually contribute to solving the math or code problem in front of it.
Okay, but let me push back on that for a second, because from an alignment perspective, isn't minimizing the divergence across the entire token distribution exactly what we want?
Well, it depends on what you're building.
Because matching the teacher's overall distribution is how we ensure the student behaves safely, predictably, and coherently, right? If we stop matching the full distribution, don't we risk the model outputting a logical but completely unreadable gibberish?
That is true if your primary goal is general next token prediction, or broad chat alignment. If you want a helpful assistant that sounds natural, yeah, matching the full distribution is necessary.
Okay.
But this paper is laser focused on specific complex domains, math, science, coding. In those areas, we only care about the neural pathways that were activated and strengthened by the instruction tuning. We want the logic, not the grammar.
Right, because it already knows the grammar.
Exactly. Assuming the student model already knows how to speak English from its own pre-training, it is incredibly inefficient to waste gradient updates forcing it to speak English exactly like the teacher. You only want to transfer the delta the exact cognitive leap the teacher made to become a reasoning expert.
Which isolates the core breakthrough, right? Mathematically defining that cognitive leap. So the delta signal is defined in the paper as log pi star minus log pi star base.
Yep, that's the one.
You are taking the log probability of the reasoning-tuned teacher and subtracting the log probability of that same teacher's original base model. You literally subtract the base model out of the equation.
Conceptually, it's just so elegant. And the visual proof they provide is honestly fascinating. They ran a word cloud analysis, applying this delta signal to Qwen 3 models across, I think, 10,000 math questions.
Oh, wow.
Yeah. And when you look at what the delta signal explicitly enhances compared to standard OPD, it isolates logical connectives. It heavily rewards tokens like hence, however, instead thus, and regardless.
It mathematically identifies the vocabulary of rigorous logic.
Exactly.
And on the flip side, it strips away uncertainty, right? The negative signals heavily penalize vague, exploratory tokens that base models rely on when they're just, trying to keep conversation going.
Yeah, the filler words.
Words like perhaps, oh, verify, and I'm just get totally suppressed. So the delta signal acts like a confidence booster, stripping away the hedging and forcing the model to commit to a strict logical path.
Yeah, and the most revealing part of the paper is how these two signals, standard OPD versus the delta signal, react to synthetically generated incorrect reasoning traces.
Oh, this part was wild.
Right. They deliberately fed the model simple math questions, but forced the reasoning down the wrong path. And the delta signal is violently aggressive at suppressing generic reasoning tokens, words like since or the variable, the exact microsecond the logic strays into an error.
Wait, so why does it catch that so much faster than standard OPD?
Well, because the reasoning-tuned teacher knows the math is wrong, so its probability for those generic tokens drops.
Okay, that makes sense.
But the base model doesn't care. It sees a sentence starting with since the variable and thinks, sure, statistically, that's a fine next phrase in this context.
Right, it's just predicting the next likely internet word.
Exactly. So the gap between the teacher and the base model widens dramatically, creating this massive negative delta.
Wow.
But in standard OPD, you are comparing the teacher to the student. If the student is weak, its probability for that token might be even lower than the teacher's.
Oh, I see.
So standard OPD will look at a completely flawed reasoning step and still output a positive reward signal, simply because the teacher's overall token probability happened to be higher than the student's.
That is such a huge flaw.
Right. But the delta signal fixes this because both models, the teacher and the base, originate from the same weights. The reasoning-tuned one is hypersensitive to logical errors, providing a much cleaner, more rigorous correlation between the reward signal and actual reasoning correctness.
Okay, but relying on this mathematically pure reasoning signal introduces a major structural vulnerability, doesn't it?
It definitely has its risks.
Because if the student model is only looking at this delta, doesn't it lose its grounding? Any ML engineer knows that if you implement a reward signal that ignores the student's current state, the training loop is going to break.
Oh, absolutely. It creates severe divergence. Theory is great, but convergence is what actually matters on the cluster.
Right.
The delta signal, denoted as R delta, doesn't factor in the student's probability at all. If you train a student blindly toward a reward signal without anchoring it to the student's actual distribution, meaning there's no KL penalty anchoring the update, it just pushes the model toward a one-hot vector maximum.
Meaning the model just finds whatever token gives the highest delta reward and tries to assign 100% probability to it, completely destroying its ability to generate diverse or coherent text.
Right. It optimizes purely for the reward and ignores language coherence entirely. In a strong to weak distillation setting, where the student is much smaller than the teacher, this creates rapid instability.
It just collapses.
Pretty much.
Yeah.
So to fix this, they introduced two specific design solutions. The first is centering. They calculate the expected rewards for a given state and subtract that from the sampled action's reward.
And for the hardware-conscious folks listening who are dealing with memory constraints, they calculate this expected reward over just the top 124 tokens rather than the full vocabulary.
Which is huge.
Yeah, it saves a massive amount of VRAM during the forward pass.
Definitely. So centering gives you an advantage function. It tells the optimizer how much better this specific token is compared to the average expected token in the top 10 to 124.
Right.
But centering alone does not fix the one-hot vector problem. To actually stabilize the run, they had to implement joint conditioning.
Okay, and this is the rule expressed as A delta t multiplied by A OPD t must be greater than 0.
Yes, that's the equation.
So in plain English, the model only applies the new delta gradient if the delta signal and the standard OPD signal share the exact same sign. They have to agree on a descent direction.
Exactly.
If standard OPD says penalize the token, but the delta signal says enhance it, the gradient is zeroed out. The update is skipped entirely.
Yep, it just ignores it.
But, I mean, this feels like a catch-22. If we are gating this brilliant new delta signal behind the old, flawed standard OPD signal, like literally giving standard OPD veto power, aren't we just diluting this breakthrough?
It does sound like it, yeah.
Right. Why go through the computational expense of calculating the delta if standard OPD gets the final say anyway?
It seems counterintuitive, I know. But it really comes down to understanding the physics of gradient descent, specifically the difference between vector direction and vector magnitude.
Okay, unpack that.
So standard OPD is actually very good at providing a safe direction. It acts like a compass, keeping the student anchored to the general linguistic reality of the teacher so it doesn't devolve into a one-hot maximum.
So it keeps it speaking English.
Right. The flaw with standard OPD isn't the direction, it's the magnitude. It wastes heavy gradient updates on useless stylistic tokens.
Oh, I get it. So under joint conditioning, standard OPD sets the compass, but the delta signal controls the throttle.
That is the perfect way to visualize it. They use standard OPD as a safety rail to ensure sign-consistent common descent. But when they agree, the delta signal dictates the magnitude.
So it pushes hard when they agree on logic.
Exactly. It applies heavy throttle to the reasoning tokens much more than standard OPD would alone, while starving the purely stylistic tokens of gradient magnitude. You get the stability of standard distillation with the sharp, focused optimization of the delta signal.
That is brilliant. Okay, so with the compass and throttle stabilized, we can look at how this architecture performs on the actual benchmarks.
And the numbers are really good.
Yeah, they built a multi-domain data set with a balanced one-to-one-to-one mix of math, science, and code, sampling from open math reasoning, open science reasoning 2, and open code reasoning. So the models really had to prove they could generalize their logic.
But they couldn't just overfit to one domain.
Right. And the results are split between models operating in non-thinking mode and thinking mode.
And that distinction is vital here. Non-thinking mode is when the model is prompted to just generate the answer without outputting explicit reasoning traces or those thought tags.
Which is usually really hard for small models.
Extremely hard. In this regime, smaller models typically struggle heavily with complex logic.
But OPD2 completely changes the math here, literally. A Qwen 3 4B model trained with OPD2 hits an average score of 70.3 in math.
That's a huge jump.
It is. That completely leapfrogs a much larger 8B model trained with XOPD. And XOPD is a state-of-the-art extrapolation method that tries to amplify the reward when the teacher is significantly better than the student, but, it still fundamentally relies on comparing the teacher to the student.
Right. It still is the base model flaw.
Yeah. So that 8B model trained on XOPD only scored 67.8.
I mean, getting a 4B model to beat an 8B model on dense logical benchmarks is just a phenomenal result. It basically proves that the bottleneck for smaller models isn't necessarily a lack of parameter capacity. It's that we have been cluttering their limited capacity with non-reasoning noise.
You really cannot overstate the value of that for researchers dealing with compute constraints. You are acquiring larger model reasoning capabilities without paying the 8B inference costs at runtime.
It's a massive win.
Massive. But the real stress test for OPD2 is the thinking mode results. Base thinking models in the Qwen 3 family are already highly optimized to output explicit step-by-step logic traces, like they're top tier. In fact, applying standard OPD to these models often breaks them.
Oh, it actively degrades them. For example, applying standard OPD dropped the Qwen 3 1.7b model from a 59.2 down to 57.1 in math.
Why does that happen?
Well, when a model is already highly optimized for step-by-step reasoning, injecting standard OPD compares its output to the teacher's full distribution. It ends up forcing the student to inject next token conversational probabilities into a rigid logic chain, which basically just breaks the chain.
Oh, it adds noise to a clean signal.
Exactly.
But OPD2 manages to improve even these highly tuned models. It pushed the Quen 3 8B's HMMT25 math benchmark score from a 44.3 up to a 52.3.
Yeah, an 8-point jump.
An 8-point jump on a highly competitive benchmark for a model that was already state-of-the-art for its size. Qualitatively, what is happening under the hood there? Why does the delta signal unlock that 8-point gain when standard methods degrade it?
It comes down to uncertainty. Because on a difficult benchmark like HMMT25, which involves really tough combinatorial math, a baseline model often gets stuck in conversational loops or hedges when it hits a difficult step.
Like it's stalling for time.
Sort of, yeah. It falls back on uncertainty tokens because the pre-training data is full of humans hedging their math answers. By starving those uncertainty tokens of any gradient update, OPD2 forces the model to commit to rigorous theorem application.
It sharpens the reasoning trace.
Exactly. It eliminates the model's ability to second-guess itself linguistically. And they proved this generalizes too. They tested it on Gemma 4 E4B and saw clear math and science improvements, meaning this isn't just a quirk of the Quen architecture.
Which is so important. Seeing a technique generalize outside the author's specific hardware and model stack is the gold standard. But, speaking of hardware, we have to address the computational cost. What does OPD2 actually cost to train? And how stable is the training run?
So the training curves are arguably the most compelling part for an ML engineer. Over their 100-step runs, standard OPD and XOPD show this familiar, heartbreaking pattern.
Oh, I know the one.
Right. The performance spikes in the first few steps, but then it plateaus, or worse, it just completely collapses. You hit step 60 and your model forgets how to do math because it has overfit to the teacher's linguistic style.
Brutal.
But OPD2 achieves a higher initial spike and maintains that high performance consistently across the entire 100-step run.
And the ablation study confirms that the delta signal is doing the heavy lifting here.
Oh, 100%.
Because if you remove the centering or the joint conditioning, the performance drops modestly because the model gets a bit unstable. But if you remove the delta signal entirely, the performance just collapses back down to standard baseline levels.
Yeah, the reasoning focus is entirely dependent on subtracting that base model.
But there is a very real computational tax for doing this. OPD2 requires calculating the delta against the base model dynamically, which means you have to run a forward pass of the teacher-based model during training.
Yeah, that's the catch. You are holding another set of weights in memory and pushing data through it for every single step. On NVIDIA H100 GPUs, this adds about 24% to 28% to the wall clock training time for the Quen 3 models.
And about an 8% increase for the Gemma 4 architecture, I think.
Right, so that extra forward pass is absolutely not free.
It's essentially a 25% stability tax up front on your compute budget. It costs more time and VRAM per step, but you are buying insurance against your model collapsing on step 60.
Which saves time in the long run.
Exactly. Over a full development cycle, you likely waste fewer training runs because you aren't constantly restarting, tweaking learning rates, and rolling back checkpoints trying to find the one magical step where standard OPD peaked before degrading. It's a tax most engineers would happily pay for guaranteed convergence.
Oh, definitely. Given that on-policy distillation usually operates in a short training regime anyway, that 25% overhead is a very practical, highly justifiable trade-off for the performance gains you're getting.
So synthesizing this, the paradigm shift here is profound. OPD2 proves we no longer have to treat our teacher models as black box oracles that we just blindly copy.
Right, we can look deeper.
By peeking inside the teacher's actual learning trajectory, by literally subtracting the base model from the instruction-tuned model, we isolate a high-fidelity, pure signal for complex logic.
We are changing the fundamental instruction. We are no longer telling the student to be the teacher. We're telling the student to learn the specific lesson the teacher learned.
And that isolation is what allows smaller models to punch so far above their weight class.
Exactly.
Well, I want to leave you with a final thought to mull over. If subtracting a base model from an instruction-tuned model perfectly mathematically isolates reasoning capabilities, what other latent capabilities could we isolate using this method?
Oh, that's an interesting question.
Right. Could you, for instance, subtract a generic chat model from a highly tuned role-play model to isolate pure empathy tokens or pure creativity tokens?
You might be able to.
The math of model subtraction and reward signaling might just be the skeleton key to highly surgical, highly specific AI alignment across any domain you care about.
It really opens up a lot of possibilities.
It sure does. Well, thank you for tuning in to this breakdown on AI paper slop. Keep experimenting, and we will catch you on the next one.